Okay, so today we're going to talk about understanding automotive electrical schematics. Again, get yourself comfortable. This is going to be a long one. Going to have some music going in the background. This is probably going to be a bad decision. But anyways, we're going to start out just with looking at a schematic and just talking about what we're looking at within the schematic and what's going on in here. So, first thing I'm going to kind of identify and talk about here is within the schematic. You'll see there's a lot of areas like here where you've got dotted lines around a component, right? So there's your component, the underhood fuse block or fuse block underhood, I guess. Just like your turn signal multifunction switch as a component has all these dotted lines going around it. Now, the dotted lines, they mean something. What the dotted lines are indicating is, hold on, I gotta make my eraser bigger so I can erase a lot more as I go. Oh, there we go. Okay. Okay, so you'll see eventually here, there we go. We get to somewhere down here where you're seeing a component, windshield washer fluid pump. Here has solid lines around the component, as does the washer fluid level switch, and also your windshield wiper motor. They all have solid lines going around it. Just as you're looking at some of the wires and the connectors that go through this schematic, and you see that some of these wires have dotted lines, and some have solid lines, and some even have solid lines which turn into dotted lines. Some bitch going on there, hey? So in these locations, what's going on there is it's really indicating that if it's a dotted line, it's telling you that you're not seeing everything that has to do with that component. So in the case of, oh, I messed it up. Okay, so in the case of the underhood fuse block, what we're looking at in this schematic is just certain components of the underhood fuse block. And generally speaking, they're going to identify the components that you see in a schematic. They're only going to put in the the items that you need to see that are pertinent to the circuit you're looking at. But that doesn't mean there isn't more to the connector or more to the component that you're looking at. As a matter of fact, I guarantee there's more to it, which is why the lines are dotted. Likewise, in a wire, something like a ground, you see ground circuit 1250 goes to ground G100. And within that, the ground circuit 1250 leaves the washer fluid pump directly, but then it goes to a dotted line, which means it's likely going to splice together at some point with other wires and connect together and then be one common ground at the G100 location. And to really identify those splices and locations, you have to go to the ground distribution schematics within your schematic realm of the world. So that's why you're seeing some lines in the schematic are dotted, some lines are not dotted, and that's really what you're looking at there and the difference between those items. Next up here, we're going to be looking at just some of the items like the connectors and the circuit numbers and such. So as we go into here, you see there's the component, or I guess a component. This is a connector. So that's a C connector X3. In the olden days, didn't mean to turn that into a eraser. In the olden days, this would have been defined as connector C3. So connector can either be a C or an X. Oh, is a banger, this one. I don't know for those of you who recognize this song. This is an invitation. Dun, 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 dun. Okay. Beautiful. All right, so we have connector X3, and you're noticing in and around connector X3, it's got dotted lines. So we're not seeing all of connector X3, we're just seeing two terminals inside of connector X3. And the two terminals that we can identify inside of connector X3 are going to be terminal H2 and terminal E2 at connector X3. Now, again, just because you see one connector X3 here, sometimes you will notice on schematics, you'll see like a section of X2, say from here to here, and then here they'd have another section of X3. So sometimes on a schematic, you'll even see a certain connector repeated a couple times just for ease of drawing and making it appear a little simpler. So at connector X3, we have terminal H2, and terminal H2 can be identified as, this is your circuit number 228, and the wire color hey, look, I put a U into it. Wire color is orange. So generally speaking on schematics, this is the information that it's going to give you, right? You have, I guess I better identify the terminal. So you're going to have, at this schematic right here, at this connector X3, you have your terminal H2, which will be a wire that is orange in color, and the circuit number is circuit 228. Now, that information is very, very fine and works out all right. Sometimes you even get, I don't see it anywhere on this schematic. I might have to check out another schematic, or maybe let's just do that anyways to look at how some different manufacturers and different IDs of wires come in place here. So looking at this one, you see how the order of things is a little bit different, but it's still identifying everything you need, right? Like there's your connector. There's your connector there, and again, that one's identified as a C instead of an X, and that would be your connector C243, and then you see terminal 2, terminal 6, and terminal 15 are identified as your terminals in this case, and this would be your circuit number, which the manufacturer would identify, and there's your wire color. Now, when you see two colors like this, the first bit is always the main color of the wire, and then the second one identified will be the tracer or the line that goes along that wire color. So that circuit 188 would be a white wire with a black stripe on it. And that's how that one would be identified. And that would be terminal 2 inside of connector C243. Some other bits of information that you can see in many of these terminal locations is you notice this area here very much identifies the terminal style as well, with this side being the female end of the terminal and this end being the male end of the terminal. Now, it's always fair to ask the audience, I hope we understand the difference there between the two terminals, and yes, it's still how it's identified, and no, there's nothing weird or derogatory about it. It's just plain normal identification of terminals, nothing more or less than that. This song's an interesting one. I don't love it. I don't hate it, but I'm just gonna skip it because it's maybe some stone sour there. I wasn't loving it. Okay, and so there's some quick terminal ID there too. Looking a little bit further into this schematic as well, you notice right in there we've got an S location. So that's the identification of a splice. And for a splice, again, in the older schematics, you're going to see an S identified. And in the newer schematics, splice is identified by a J for a junction at that point. So newer ones will be identified a little bit differently than the older ones. And the other part, here I got this one kind of just to identify these differences. Your connectors can be, again, your C or your X, and your splice connection will be an S or a J. Now, the splice connection, if you just see an S or a J on their own, that's essentially you have your wires coming together, and you have the strands all twisted together, and they're all soldered up really nicely, and that is a splice, right? Like that is just an actual splice, so that would be identified as, your J 102 or whatever number. I'm just making this up. However, you can actually get a connector that can disconnect and reconnect that has a comb end in it, and it is known as a JX, or essentially a splice connector. And this connector is a mechanical connector that you can disconnect and reconnect. So if you see a JX, it would be that way. And a lot of times you see these in a low speed single wire network, star type of network. And you'll see in this single wire star type network, a bunch of these wires coming into a connector like this, and then your top to your connector would simply be a comb that would connect all of these wires together as one fruitful unit. So when that connects up together, all of these are spliced together. Which means, so you have a JX is an excellent testing point, because you have a point where you can disconnect your splice, go through all your different areas of your splice, and then you can test each wire individually, making your diagnosis considerably simpler and faster. So I do like splice connectors a bunch, where an actual splice, you would have to cut and resplice together, making a bit of a pain in the ass. And then connectors, again, are just connectors most of the time, carrying your average, signal or monitor input output type of wires. The component locations is, when we're looking at these schematics, I guess I won't go there. I just want to show a splice and a splice pack first that are, wonder if we have any of these identified here. Yeah, not really a good one, just that one splice we looked at. Oh well, you're out of luck. Component locations, when you look at different connectors and different identifications of items, you're gonna see that many of the connectors and such will have some sort of location on them. I'm trying to find one that has a few variable ones. A little Pantera here, not bad. It's not. All right, there we go. Okay, so looking at this schematic here, this is a decent example. Because you have to kind of find locations of connectors or splices. And if we look up here, S236, so that 200 designation for the splice So it's in the 2XX range, right? So your 200 designation. And here you have a series where there's your C120, C131, and P100, where these are all in the 100 designations. Well, that first digit, that first identifier of 1 and 2, that becomes important in identifying just kind of a general realm of where these things would be located within your vehicle. And just going to show you that. This has to do with the component locations in the vehicle. So there's standardized locations within the vehicles, and this has to do with those numbers. So this would be your 100 series would be there. Your 200 series are going to be, so 100 series we can consider under hood. Your 200 series is instrument panel. Right, so this is the vehicle like traveling this way, right? Your 300s are your passenger compartment. Your 400s, you can either consider your ledge, ledge and trunk. Or if it's a truck, it'll be your truck box. And then your 5s, 6s, 7s, and 8s all become your doors and your doorways. So your 500s are your driver front, your 600 is passenger front, 700 is driver's side rear, and your 800s are your passenger side rear. And then finally, your 900s belong in your kind of your tail light, your rear bumper area. Okay, so now that we have kind of a rundown of what we're looking at inside of the schematic, let's get a little more technical with some of the wiring and some of the distinguishing what's going on inside of the schematic. So the first thing I really like to try to identify is kind of the inputs versus the outputs inside of the schematic. So a lot of that type of information will start at a control module. So the control module, the main control module that's in charge of whatever circuit, whatever item you're looking at or you're analyzing, that's where I like to start, because essentially the body control module is going to be the one who's going to make decisions. And for the body control module to make decisions, it needs to know information, and it needs to receive information, and it also needs to give a command and turn something on or off, or create some activity or not. And for the BCM to do both of those, it's going to have a series of circuits simply known as your inputs and outputs. And your inputs is going to be the series of circuits that will inform your body control, or whatever module you're looking at. It will inform your module what to do, and the outputs are going to be your body control module actually turning something on or turning something off. So in looking at this specific circuit here, we're going to go through kind of all the different areas of this circuit and what's happening in there. But the first thing I want to identify is these units right there. And these units are going to be monitors, which will allow the computer to receive an input from a switch or from a sensor or from something external to the computer, so the computer can know what's going on. In the case of your home computers and such, this would be your keyboard. So this would be how a computer can understand when you're pressing that keyboard button. This is how the computer knows that you're actually pressing the keyboard button. And I'll explain kind of how that one works in a little bit. I just want you to identify it. Sometimes you can see this as a source of information, and this is that up-down arrow identification is going to be a data communication stream. So with your data communication, again, identified there, goes to your instrument panel cluster. So even just looking at that data that would go about the windshield washer system, which would go from the body control module to the instrument panel cluster, this would be some sort of identification on what's going on in the system, and if you have enough or not enough windshield washer fluid. So if your fluid level switch is monitored low, then it maybe could inform the body control module of that, or something along those lines. I'm not sure. We'll look at the big picture to see all the details of this one. Okay. So those are, generally speaking, excuse me, going to be how your inputs are identified. Now those inputs could be identified as a monitor like this, or it could be identified as a monitor which will be a ground side monitor. Then you're going to see items like these. And these items are essentially output drivers. Which means this is your computer that can control what's going on there. So your computer will close this switch or open that switch, and it's up to your computer to make that decision, and it's going to make that decision based on the inputs. So whenever you see any switches like these are the computer actually applying a switch or turning something on and turning something off within the vehicle. Now, in a case like a windshield wiper circuit like we're looking at here, if you follow these wires, you're going to notice that inevitably the majority of them show up to a relay, right? So you have a relay there for those two grounds, and then this power wire coming around here, whoop, 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 goes around there, and it's going to supply power to a relay. So you notice that in any case here, the computer, at least in this scenario, as far as your output drivers and in your windshield wiper washer system, all the computer is doing in these cases is going to be turning on relays, turning on or turning off relays. And just so you're aware, like a relay, the current draw in a relay is quite small in a normal automotive relay, maybe to a maximum of 20 milliamps, right? So a very, very small current draw, because that relay has, quite a high resistance. Realistically, I think we're probably closer to 10 to 15 milliamps. So the current that the body control module actually has to command through these circuits is quite low, not a real high current, which makes it able to turn on those relays, effectively and quickly. And then the high current that's required for this circuit will then come through the relays and the relay switches themselves, so that the computer doesn't have to deal with high current. The computer is only dealing with low current, and yet we can still supply high current to all the load devices that's required. So the first thing that we kind of need to identify very, independently of each other is this whole input-output type of scenario within the module and within the schematic. Now, I see that there's 3 monitors there. Those monitors are connected to a ground here, and with that ground being there, if you just have a straight ground through a computer, through a module, that would normally be described as a discrete ground. And it would use a discrete ground for a couple reasons. One reason, because it's a very clean ground, it doesn't get a lot of interference or noise with it. And then the other side of the coin, the module could use that discrete ground for diagnostics. So it would know if there's current going through that circuit or not. It would be able to do some self-diagnostics and determine if the wire is in decent shape and it's actually connected to itself. Creator. They're fun. Okay. I'm not sure if many of you would describe that as fun. So, right off the bat, we look at this turn signal multifunction switch and how it feeds into the body control module. That whole section is an input to the module. So that your turn switch, your multifunction switch, again, you're only seeing part of it because we're only seeing the windshield wiper portion of it, not the turn portion of it. But it is physically you, the human, turning the switch and manipulating the devices within the switch to send a signal to the body control module. And the other input that becomes part of this schematic anyways is a little switch in the windshield wiper motor, and it doesn't actually say what this switch is for, so you almost have to know a little bit about this circuit or some descriptions in there, but that's going to become your park switch. And this is going to be how your computer, how your body control module will actually know when the windshield wiper motor has hit its park position and that it's into its park position completely. So you have a couple inputs into the body control module. One series of inputs is the ones from your multifunction switch that you're going to be manipulating and modifying to input in the body control module, and the other input into the body control module is straight from the windshield wiper motor, and that's going to be your park switch telling the body control module when to park. Okay. Now inside of your multifunction switch, I wonder if these guys are right. Do you think Satan is real? Okay, you see an item like that, pretty fancy drawing. That little S identifier there, that means that this is a rotating switch. And the V here means that it's a latching switch. So when you think about when you're turning your windshield wipers on, you grab your windshield wiper switch, you'll rotate it. In some cases you rotate it, at least for General Motors you do. Some cases the whole lever moves up and down. But you would rotate it, and where you rotate it to, when you let go, it latches, it stays in position. So in your schematic, that little squiggly line with a V in it is the indicator that you have a rotational latching switch. Meanwhile, over here, you see this switch here has an evil E to it. And that evil E is a push style switch, and it's going to be a momentary, meaning it will not latch, it will spring back. So now you have a push style momentary switch. And again, in these old style or some of the General Motors that this schematic is from, that's going to be your push button in the end of the lever, where you push it in, it does your little squirt, and then as soon as you let go, that button pops out again. So these are literally the electrical schematic identification of what's going on inside of your multifunction switch. Now, when you're rotating your switch itself, and you think about the rotation of the switch, you have another dotted line inside of here, and that dotted line simply means that when this switch here, I should change colors so I'm not doing the same color as the schematic. Okay, this switch here and this switch here, there are two switches within the unit, but they both will move together, right? So if both of them are moving to the right, then they both move to the right the same amount. If they both move to the left, they both move to the left the same amount. So the dotted lines that you're seeing in these little locations here, they simply mean that these are associated together. So a coil of wire here, when you engage the relay, will pull on that switch and close that switch off. In the case of your rotational latching switch here, when you move it, it's also going to move this lever. So it just shows the association between the things and that they're connected. And you have to read into it a little bit to know how they're connected that way. So this lever here and this lever here will always move the same amount in the same direction. And in many vehicles, when you twist backwards, or in these style anyways, when you twist backwards, it does what's known as a mist. And the mist would flip that switch to those locations. So now your switch would be in that location, causing these circuits to happen. So let's follow some power ground kind of distribution here and figure out what's going on. So first of all, we have a reference voltage that's going to be supplied at the monitor. And then we have the monitor itself here, and then we have a fixed resistor in the middle. That guy, essentially, if we were going to look at it as a regular drawn schematic, we could have a 5-volt reference go through a fixed resistance inside the module. So that's all inside the module, right? From there you have this little arrow coming out, and that arrow becomes important. So this is essentially your monitor circuit, and we're just going to talk first about how this multiplex signal works, and then we're going to go talk about the monitor in a little bit. So that's part of the circuit. Now, if we follow this circuit through the fixed resistor, past the monitor, we're going to go to a 332 ohm resistor here. So I'm going to draw another resistor in my circuit, 332 ohms. And then we continue following this circuit. If you notice on this end, going this way, all of the circuits result in a dead end. This one, remember that's that switch there, dead end, and then this one results in a dead end. So any of those settings here automatically result in a dead end. So I'm not going to really worry about that portion anymore. And we continue following this circuit, whoop, along there, and we get to our missed input switch that you've inputted with your hands. Continuing on from that switch, it finds itself a ground within the module. So essentially, we're going through a 332 ohm resistor, through the switch, which is closed, back to the module to ground. And essentially, when I get rid of a lot of the noise around here, there we go. And I get rid of all this drawing here, and you look back at this circuit, essentially, this is just a simple 2 resistor circuit where if we were able to measure the voltage drop across that resistor, we would get some sort of resistance. Who knows what the resistance is, because we don't know what that resistance is, but we know there's 2 resistors in the circuit. And we know that the circuit will expand to get higher resistance because we can see there's higher resistances in the circuit. So very likely they're going to get to higher resistances. So if I was just to analyze and think about this circuit, I would probably say that this one would be pretty close to a 0.5 volt drop over that resistor. And then this one would probably have the remainder of the voltage being consumed over that resistor. And I mentioned that because this is how the computer determines which switch was pressed. Not necessarily, the computer knows the numbers, but we don't necessarily know the numbers. However, we can figure it out quite easily. And when we look at this voltmeter here, if we look at the ground leg of this voltmeter here, it's essentially connected to ground, right? So if I could redraw this voltmeter and just connect it to ground right here, that would speed things up. And then this end of your voltmeter here is connected to that side of the resistor. So again, why don't I just connect it right there, and I bring the voltmeter, instead of having the voltmeter right over the resistance inside of the circuit, I'm now putting my voltmeter right beside this resistor and then placing it inside of a computer. And then that voltmeter would still be reading the same reading of 0.5 volts. This is precisely how your computers are able to monitor. There we go. Hold on, need another sip of coffee. We can skip some Kim Mitchell. I don't know. Why not? Oh. All right, here we go. So kind of looking at monitors and understanding monitors and what's going on there, essentially you're only going to see a couple types of monitors like this. Sometimes you do see a positive/negative monitor for monitoring an AC circuit, say directly from a knock sensor or something along those lines. But most of the time, your monitors are going to look like this. And these are inputs. So again, anytime you see a drawing that looks like either of these two, this will be your way that your computer can analyze what's going on inside of the circuit. So first thing here, identifying number one, you have your current limiting resistor or your fixed resistor. So this is a case where you're having your voltage being applied to the circuit, and you might have some sort of switch that goes straight to ground. And in a circuit like that, where you're supplying some sort of power through a switch straight to ground, if you look at this, there's no circuit protection. There's nothing keeping the current down to a limited amount. And when you're thinking that you just want this to be a circuit where your computer can see what's going on, you don't really care about how much current goes through the circuit. You just care about the signal that arrives there. And so in this style of circuit, very much that resistor is going to be for current limiting processes, right? That's going to be to limit the current so that when this switch closes, you don't have too much current coming out of your module, damaging your module. So it's a current limiting resistor when you have an on-off type of circuit. So whether it's a digital signal, whether it's just a switch or something like that. And in our I don't have too many monitors there. I guess I'll just go back to this one. Okay, so in our circuit like this one, you see in a case, all right, there we go. In a case like this one, you have your monitor which goes straight to a switch, and then from that switch, straight to ground. So that is literally the circuit that we've just identified above, where you can have an input that goes straight to ground. And in a case like that, you absolutely require that resistor that's located there to limit the current and prevent any damage to the body control module. So that's going to be your first example of why that resistor is required. In the other scenario, you're going to have a circuit like this where you have your reference voltage, and then you have your resistor here, and then you're going to have another resistance at this one. And in our previous example, it was a 332 ohm resistor, but it doesn't matter. It could be even just some sort of variable resistance, maybe a temperature sensor. And a temperature sensor, of course, is an NTC device. So when it gets hotter, negative temperature coefficient. So as it gets hotter, its resistance will decrease. And as it gets colder, its resistance will increase. So if the resistance, if it's cold outside, cold, the resistance will increase, which means the voltage drop over this unit would also be quite high. And again, in most automotive circuits where it's variable, the high end of the range will be in and around that 4.5 volts. So inside your module, you would again have your voltmeter. Oh, I've had this song in my head for so long. I saw a video of these guys doing a show like just, oh gosh, just like a month or a couple months ago or something like that. Anyways, they're rocking still, eh? That old COC, what a solid band. Every time, knock me down. There it goes. Okay, so you have a voltmeter here connected to ground. That voltmeter is essentially going to read the same as, again, if you put a voltmeter right across here, because you have one leg connected to ground and one leg connected to this side, essentially, of the fixed resistor. So your voltage monitor in here, now your voltmeter here would be reading approximately, the same voltage drop that would be over top of your temperature sensor itself, your negative temperature coefficient temperature sensor, your NTC. So in this case, you would have your fixed resistor here. You're not so concerned about it limiting current, because the only time you would be damaging your module from current without that resistor is if the temperature sensor was shorted to ground. So as long as your temperature sensor or the wire going to your temperature sensor is not shorted to ground, then you should not be concerned about too much current. Therefore, the resistor then inside of the module just becomes a fixed resistor just to divide voltage. And that's what so fixed resistor for voltage divider circuit. So this, it becomes a fixed resistor for the voltage divider circuit when you're dealing with a variable resistance or a variable signal on the other end. It's going to be a current limiting resistor when it's an on-off signal and that signal is turning, making things happen. Okay, your reference voltage. Reference voltage is essentially number 2. Now, it only has a reference voltage inside the module. A lot of times inside the module, it will identify your reference voltage. And sometimes you'll even see something like that, like 5V3. And this would identify that it's going to be a 5-volt reference circuit, and it's going to be the third 5-volt supply circuit. And what this kind of means is inside your module, it's going to have a few 5-volt supply chips in there. And each of those 5-volt supplies will supply several sensors or several monitors, inputs. It can only supply so much current, so eventually it's going to have to get another 5-volt reference supply to supply a bunch of other circuits. So essentially the more inputs, the more monitors, the more sensors a vehicle has, the more 5-volt reference circuits that you're going to have. And current model vehicles have some pretty big 5-volt reference circuits going on in there, 4 or 5 different 5-volt reference circuits. A lot of times they do some unique wiring, like in an accelerator pedal position circuit. It's going to have 2 potentiometers for redundancy, and each of those potentiometers will be fed a different 5-volt supply circuit. So even if the vehicle loses one of the 5-volt reference circuits, the APP will always work. Anyways, yes, just some interesting stuff there. So essentially, when you see just a line with a dot, it's identifying. Oh, sorry, Lemmy. I didn't mean to turn Lemmy down. I even got some Lemmy chops going on these days. So It's just meaning that it's going to be a reference voltage quite often lower than what your source voltage is. So a lot of times you'll see some numbers like 10 volt, 8 volt, 7 volt. Those are some popular numbers, but by and large, without a doubt, 5 volts is your common reference. And 5 volt as a reference voltage, just so you kind of understand the scope of what we're dealing with, it's the common reference voltage for many of the sensors which work with CAN networks. So we're talking everything from, you know, all the machines, your phones, elevators, all these different types of things, vehicles, almost everything's running 5 volt references anymore. The nice part about the 5 volt reference is even if your battery voltage goes low, say your alternator stops working or things, see ya, have fun. Things stop working, your battery voltage goes down to 11.5 or 12 volts, still considerably over your 5 volt reference supply. So your sensors never get a compromised signal, even if you have a voltage go that low. And quite honestly, you drop below 5 volts, your vehicle's not running anymore. So you don't have to worry about that happen. So it's a nice stable voltage, at least for automotive usage as well. Number 3 here, kind of identifying a ground. This is really just to say that if you're supplying a reference voltage within the module, then that means your monitor is, you know, if you can consider your monitor being that voltmeter going to ground, I'm gonna have to draw the 4 back again there. Your voltmeter going to ground, then in a case like this, if this circuit were grounded right now, the voltmeter would read that 5 volts. And I got my pull up, pull down backwards here. There we go. Okay, so right now, let's say we have, I'll draw the remainder of the circuit here. Okay, so we have a scenario like this. There's gonna be no current going through that switch because the current's blocked, which means at the voltmeter, we're going to be reading the reference voltage and the ground. So we're going to be reading a 5 volt potential and a 0 volt potential. The voltmeter, of course, reads potential difference, your 5 minus 0. So you get a 5 volt signal at the voltmeter there. Now we could identify that with our monitor as when the switch is open, we're going to have 5 volts. Then when that switch closes, now regardless what closes the switch, whether it's a person pushing a button or, you know, the park switch inside of the motor, or some different types of inputs in an encoder motor, something like that, a Hall effect switch, who cares? When that switch closes, now, it's going to provide a ground potential on one side here. So this side now has a ground potential, and if we still had a voltmeter to ground here, this would also be a 0 volt potential. So of course, your voltmeter would read 0 volts, being in the middle here. So we could say when the switch is closed, we have 0 volts. So essentially this circuit is known as a pole down switch because it's pulling the switch is pulling the voltage down, right? When the switch closes, pulls the voltage down. So that'd be identified as a pull down switch. And that is the majority of the types of circuits that you're going to see within a vehicle. Occasionally you will see a pull-up style of circuit like this one, where it will be grounded inside the module. And a lot of times these are going to be just simply not necessarily something that the computer has to module or has to monitor for an activity, but just something that it's a nice to know type of deal. So in an example down in our schematics here, I don't even know if we have any. Oh, there we are. So you see right here, we have our park signal. Right, so there's an example of one of the monitors that's going to behave a little bit differently. And your park signal, when we look at this schematic, it's hot in run and start, goes through a fuse to your park neutral switch, closed in park only, and then automatic transmission shift lock controls. Right. So realistically, your transmission is going to need to know that information. It needs to know what's going on in there. However, you would need to know, just the transfer case would need to know if you're in park or not in park, because of course shifting into low requires you to have that input. So this input as a park signal into the transfer case control module is really just so the transfer case control module knows whether it's in park or not. And the power feed going here into your transmission is required for the transmission itself. And now we just tap into that line for the transfer case shift control module in order to supply that signal. So there's an example of that one. Okay, so this one, again, if this was a voltmeter connected to ground, it's going to read 0 volts all the time. And as soon as this one is being supplied battery power or a signal from, in the case we just looked at, the park input, it's going to supply battery power from there, causing the voltmeter to read 12 volts here, causing the voltmeter here to read 12 volts when that switch closes. So this would be a pull up switch scenario. Okay. And again, I explained earlier, when you see a ground inside of a module, it's going to be, if it's a ground for one of your inputs, it's going to be called discrete. And it's going to be clean. So in essence, no voltage spikes. Hopefully. Cleaner. So it will be clean, and then also it can use that for diagnostic purposes. Meaning the module can monitor whether there's any current going through that circuit to determine if the circuit is in fact intact. Now your monitor circuits, I spoke about this on-off type thing. So as far as your monitor circuits and your on-off type circuits go, that's where your pull-up, pull-down switches type circuits operate, and that's what they're talking about with that. As far as your monitors for a multiplexed or for different types of signals that could come through one monitor, I'm going to draw the resistor like they're supposed to be drawn now. And I'm going to draw my monitor. So this would be inside of the module. And from that, we could have a variable resistance here, which will then have a discrete ground. So we have a fairly simple circuit here, which we're just going to kind of analyze and break apart a little bit. I was going to say we got variable resistance, and I was going to say a throttle position sensor, but I didn't draw a potentiometer. I just draw a variable resistance. So I'm going to go back to saying this is a temp sensor. So this is a temperature sensor, and again, NTC, which means when it's cold, it's high resistance, and when it's hot, it's going to be low resistance. Now, your module will have your 5-volt reference, and 5 volts will be sent out of this circuit, going through your fixed resistor, past your monitor, so through your fixed resistor, past your monitor, through your temperature sensor, and then back to the module for ground. Now, depending where your temperature sensor is in resistance will depend on the different voltage drops. So in order to just give an example of this, we're going to use just a series of fairly simple divisible numbers here. And I'm going to say when the cold being high resistance, let's say that's going to be 1,000 ohms. And when it's hot, being low resistance, let's say that's going to be 10 ohms. And then I've just kind of identified the fixed resistor around 100 ohms. Again, just numbers divisible by 10. So when we look at the circuit like this, when the circuit is cold, essentially we're going to have a 5 volt supply go through a 100 ohm resistor, and then it's cold, so it's going to be 1,000 ohm resistor here to ground. Now, without looking too much at these numbers, if you identify that the voltage drops are going to be kind of a 10-to-1 going from one to the other. So we can do the math on this, but I'm going to choose not to, because what you're really going to realize is it's going to bring you pretty close to this resistance will bring you to around a 4.5 volt drop, and this resistance will bring you around to a 1.5 volt drop. When you look at this circuit in the way that it's drawn above, that would mean here, when it's cold, the computer's going to see 4.5 volts. Right? All right. Next, when we're kind of in that middle or moderate temperature, let's say we're going to be around 200 ohms. So then we'd have a circuit at moderate temperature. I shouldn't have erased that part stays the same. At moderate temperature, let's say our temperature sensor be around 200 ohms. Now, that one's going to be twice as high as the other one, so its voltage drop is going to be twice as high as the other one. When you're looking at, again, a 5-volt circuit, and we don't have to be crazy accurate, you can say, so we got, around 3.5 there and around 1.5 there. Good enough. As long as you see that the voltage starts decreasing throughout the middle of the range. So that's, somewhere in the mid, we'll say that it's around 3 volts. When we change this, nice, there we go. When we change this to a full hot engine, and this gets down to 10 ohms, now this resistance will have about a 0.5 volt drop, and this resistance will have a 4.5 volt drop. And again, the computer is going to look at that as when the engine's hot, we're going to have around a 0.5 volt drop. So all in one sensor and through one monitor, the computer is able to determine the temperature of the engine based on the resistance of the sensor outside of the engine. And I shouldn't have drawn all over that because I was going to kind of show one. And under normal operation, you notice that all of our voltages remained between that 0.5 and 4.5 volts. So in a variable type of circuit, it's very much going to be, that's the go, no-go zone, right? So you have 0.5 volts all the way up to 4.5 volts. This is good. This is good for a variable voltage signal. If it was an on-off signal, this would be bad because an on-off signal expects to be either 5 volt or 0 volt, as we've decided before. So for an on-off or a digital signal, this is good. You would not want to see either of those in the other scenario, meaning you wouldn't want to see anything but 5 or 0 in an on-off. Otherwise, that's 12 or 0, or full voltage or 0 would be a better way of saying it if it's an on-off circuit. Likewise, in a variable resistance circuit, you don't want to see the circuit go above 4.5 volts or below 0.5 volts. And in order to just kind of identify what's going on there, we kind of have to have some circuit faults in there. So what could happen in a circuit to have a fault here, how do I get, there we go, I want to go to red again. Dismiss error, yeah, I don't know what's happening there. Okay, so let's say right here we've got a short to ground. So this is a fault. We've got an issue in this circuit. If your monitor here is looking for something going on, well, what's going to happen if that's a voltmeter to ground? Then that means you're going to have both ground potential here and ground potential there, meaning it's going to read 0 volts. So you get 0 volts. In this case, your signal is shorted to ground. There we go. Clean it up a bit. Okay, there we go. Fixed up my circuit again. And very importantly, while we're listening to Typo Negative there, great tune, great tune. Okay, so in this circuit here, so if the signal shorted to ground, we saw that it ended up below that 0.5 realm into that 0 volt realm. When the signal here, let's say, gets cut and we get an open in the circuit, and so now we have an open fault. And we look at the circuit now, well, now we have a 5 volt reference going through a voltmeter to ground. Well, now in that case, it's going to read 5 volts. So this becomes an open. Right? So again, you have a circuit that in normal operation for variable resistance should be between 0.5 volts and 4.5 volts. If it goes above that, in this case, it's an open. And if it gets shorted, then it will go to 0 volts or drop down below that. And that's essentially the monitor. That's how the monitor is able to determine if something's wrong with the circuit. It can tell you whether the signal was shorted, whether the signal's been open, and then you have a series of poor performance codes, which are just not giving a signal which you'd expect. Meaning, if you turn your key on, in the case of a temperature sensor, when you turn your key on, you've got engine coolant temperature sensor, you've got ambient temperature sensor, you've got your transmission fluid temperature sensor, intake air temperature sensor. You've got lots of temperature sensors. After the vehicle sits for a while, the computers do a self-check and they determine if all the temperature sensors are reading the same amount. If they're not, then it could probably say that one of your sensors might have a performance issue. So that's one way that you might get a performance code. Okay. Okay, back to our schematic. This is a long one. Okay, so inside your schematic, you have the ability to tell what's going on and at different voltages through your monitors. And if we looked at, again, this multifunction switch and the different positions it can be in, if we moved it to this position, this is where you turn it essentially from off to on. And that off to on becomes your intermittent setting. So if you can kind of figure out your different settings as far as where you would put your windshield wiper, you can have your intermittent setting, and then you have your on low setting, and then you have your on high setting or fast setting. So those are going to be the positions that we're going to look at inside of here. So the first one we're going to look at is the intermittent position. On this side of the circuit, it does nothing, and we'll explain why that one becomes important later. And on this side of the circuit, again, we're going to go now through our intermittent settings. And in this case, these intermittent settings go up and they go through one. Oh, here we go. Hold on. I got to do this better. 1, 2, 3, 4, 5. By the way, all you young kids who might be learning and studying, and you love that band Sleep Token. I'm kind of hit and miss with Sleep Token. I think they have some songs that absolutely blow and some that rock, but they do kind of this long flowing melodic type of interesting thing, and to me that's this band, Opeth. I highly recommend, if you like that Sleep Token, check this band out. They're awesome. To stay. Okay, so looking at the circuit in its current setting, we would be going through all those different resistances, which means this would have a fairly high voltage drop. So your monitor here would read a fairly high voltage drop at that point. Your switch here is your selection for how fast of an intermittent you want. Do you want your intermittent to have, a short rest in between each sweep or a long rest in between each sweep? And essentially, this is where the computer will determine the different voltage drops for which setting you choose. So this lever here, that's your choice. That's where you're choosing to set that switch, and every time you move it along these lines, it's going to go through fewer and fewer resistances, and when it goes for fewer and fewer resistances, the voltage drop at this point will continually diminish, essentially giving you a different selection for speed. So if we went back to the monitor here, we might say, okay, well, we have, how many speed selections do we have? 2, 3, 4, 5. Okay, so we have 5 delay selections. And out of the 5 delay selections, you're going to have, your fast, slow, mid, and then the in-betweens. Almost fast and quite slow. And essentially, say if you selected fast, that might be your 4.5 volt drop. If you selected slow for your monitor, that might be your 0.5 volt drop. And then these in between might simply be a 1.5 volt drop, a 2.5 volt drop, and a 3.5 volt drop. So regardless of which selection you take, your monitor at the computer is going to see that as a different voltage. And inside of your computer, there's going to be programming in there that will say, okay, if I see anywhere between 2.25 and 2.75 volts, that means go to mid speed. And then the computer will command its outputs to command that mid speed. So it gets the input from you, will turn around and command those outputs to create it to go. And so that's how your computer is then able to determine which speed for your delay, and then of course turning it to your intermittent. Your next level is simply going to be turning on the windshield wipers. So now you're turning your windshield wipers on, and in this case, it's still blocked, nothing's going on here. And in this case here, it's essentially going to the same one as if we selected mist, which makes sense because when you turn mist on, you only want it to do one sweep, you let go, it stops sweeping. If you hang on to mist, it'll actually continue on the slow speed because it's going through the same resistor and it's given the same input to the body control module. So the body control module cannot distinguish between the miss setting and the on setting. The difference is in the switch itself. One of them springs back and the other one latches, right? So the one that latches will remain on, keeping your wipers on low, getting there. And low might be, in your voltage drop setting, it might be actually, the lowest. It might say, it might be 0.2 volts or something along those lines. So when the computer sees an extreme low voltage, then it'd be like, oh, okay, there's a very low resistance up there, must be on or hit the mist, right? So mist will be momentary, on will remain on. Your next speed that's available becomes your high speed. Now for your high speed, your module needs a different input to distinguish between low and high. Again, it doesn't need to distinguish between low and mist, but for high speed, it actually runs the wipers on high. And that's going to be the only reason that terminal K on X3 in the turn multifunction switch exists. That's circuit 1715, because in this case, your terminal here would simply have still that same resistor being passed through. So this one, it just says, okay, we're going to be turning on. And now the input into this one, again, just being an on-off type of input. So again, it's going to pull the circuit down to ground and be that pulled down circuit. And as it pulls that down, it's going to read that as the monitor is switching then to ground, going to that 0 volts, meaning in the computer language, this is fast. So now the BCM can go over to these switches and start turning on some outputs. Right? So your inputs is all that turn signal multifunction. And if your body control module doesn't get any inputs, it will never command an output. So two things you can do diagnosing. One, you can put a voltmeter at these locations and start monitoring the volts as you manipulate the switches, right? Start monitoring the volts as you manipulate the switches to determine if your multifunction switch is in fact functioning and sending a signal to the body control module. Also, and one of my favorite methods of diagnosing a switch or if something's working, go into your scan tool data and look for the data for this switch and simply start manipulating it and see if the body control module is sending information to your scan tool. Because that's the only way it can get to your scan tool, through the multifunction switch. So if you can manipulate the switch and see it on the scan tool, then you know these monitors and this ground are functioning correctly. You've essentially just determined that all your inputs are functioning correctly through your scan tool input. Oh, let's just listen to that double basing. Oh, beautiful. This is a Bleed by Meshuggah. This is one of my unicorns. This is a song I'm trying to learn to play. It's a tough one. Okay, so the body control module can now command on one of the output drivers, either a high side driver or low side driver, to determine what to do. Now, it doesn't mention it inside of this body control module, but if you follow the circuits up and you look at the relays they're connected to, it's telling you what relay that it's functioning. So windshield washer is for this one. So this output driver is essentially the command to turn the wash on. So that'll turn on your windshield washer relay. Sometimes you will see that PCB. This means printed circuit board. So your printed circuit board relay essentially means this is not a mechanical relay. You cannot physically pick up this relay and pull it out of the fuse block. It's part of the fuse block, and if it fails, you need a new fuse block. Interestingly though, there's one of the diagnostic scenarios I hear quite frequently from people is, well, it didn't have power at the fuse. Take a look at how these fuses are wired. That fuse is powered up through a relay. This fuse is powered up through the battery. If you tested these fuses and just searched for power, one of them would have power and one would not, and they would both be working and functioning correctly. Don't always assume that a fuse should have power. A fuse should have power when it should have power, and that's the only time it should have power. So don't get caught in that one. So your first output driver there is a ground side driver or a low side driver, and it's going to control your washer. And then you have your second one here, which is going to be your high function. And then this one here is going to be the one we're going to look at first as the low function. Oh gosh, he's tight with those drums, eh? Listen to that double bassing. Beautiful. Absolutely gorgeous. Okay. Let's get this done with, Matt. Okay, so what's going to happen? The computer gets all the inputs required. It's going to turn on the windshield wipers, and the on signal is going to be sending power through here, and it's going to power up your windshield wiper relay. So that relay, that's a sign of a coil. It's going to power up that relay. I love this part. And that goes to G200 ground. 200, so that's in the instrument panel. Right, so in that cluster instrument panel area, which is interesting. Why it grounds out in there anyways. Because it's part of the underhood fuse block. So it must be sharing a ground with something else for convenience and cleanliness. So that's going to turn on your relay. Hello, Dash Boy. That's going to turn on your relay, which will cause this switch to make connection here and open connection with this one. So that'll become important later on. Okay, and as it goes through here, we go to terminal D at the windshield wiper motor, and holy crap, 2.5 hours later, we actually turned on our windshield wiper motor finally. And through your windshield wiper motor, you see down here that the motor itself finds a ground also through that G200. So they share the same ground, the relay and the motor. And of course, this one here is just your park switch so that the computer knows when you're turning it off. You turn the windshield wiper motor off, the computer will run the windshield wipers all the way down to the end, right till they park, and ensure that they sit really nicely for you. So that's just the acknowledgement of the park switch for you. And there is your low speed operation of this circuit. When you turn it to the high speed, it's going to turn on this high speed driver, and the low speed driver is still engaged. It won't turn off the low speed driver, but it's also going to turn on the high speed here. And as it turns on the high speed, it's essentially providing a ground, because this is a low side driver. All right, so we see right there that it's supplying a ground. So it's a low side driver supplying a ground to this relay, and the relay itself is being supplied power from the battery. So we have power, we have ground. Now that the module turned it on, so that relay is going to turn on, which will cause that to close, and then cause, whoops, I didn't mean for that to go to an eraser. Okay, cause that to close and cause this, what the shit? Cause this to open. There we go. Pretty impressive. Okay. Now, the interesting part about this circuit here is now that that one has closed. Oh, no, it does turn off. It does, sorry. This guy goes off. Coming straight from it. Probably. Whatever. Whoever's still listening, you're gonna hear some of this song. So this relay turns off, which means this one is receiving power in quite an interesting way. And the way I'll kind of identify this is coming back from the windshield wiper motor. If we follow this circuit, it goes through that relay and then through the wiper relay in the off state. So in the on state, it's providing power to the motor in the one location. In the off state, it's providing power in the other location. What happened here? Something's wrong with this circuit. So we have power and ground, but how's my high speed getting power? Something's wrong with this circuit. Well, the low speed worked just fine. We're not going to worry about the high speed, I guess. But we will look at the washer. Okay, so in the washer input, again, you get your input from your multifunction switch there, and quite simply, in the washer signal, it's going to close this low side driver, and that's going to provide a ground for the relay. And again, that relay's provided battery power, which closes that guy up. Oh, there we go, which provides power through here, through the windshield wiper fuse. To to your washer fluid pump that's grounded out, and that's how it's going to turn on your washer. So I'm going to be done from now because I'm running out of energy, but I'm going to go through just schematics on their own in the next few videos here, just to kind of give you a rundown of what's going on. So anyways, hope you enjoyed, and take care.